Hey AP, in this video we're going to talk about bond enthalpy. So this word enthalpy has come up a couple of times now in our work that we've done the last couple of days. Enthalpy is shown as delta H, and enthalpy is different from Q, and that enthalpy is equal to the amount of kilojoules required per mole of substance that you're looking at, whereas Q is something that's usually just in joules or kilojoules. And it doesn't matter how much of something we have. So if we're using 1 gram of something, we say this is how many joules we get out. That's our Q. But when we're looking at it in terms of moles, like the molar enthalpy, then we have kilojoules per mole, and that's delta H. So just a little nuance as to what you're looking at. So delta H, kilojoules per mole. Q is just in joules or kilojoules. So bond enthalpy, we know that atoms are attracted to each other. We know that the electrons in one atom are attracted to the protons in another. They have an attraction for each other. That's how they are stable. They come together and they stay together. So this makes the molecule stable at a low energy, and this energy is potential energy because it's about how close they are together and their attraction between them. If atoms are forced to be too close to each other, they're going to begin to repel because now their protons are coming in contact, one proton from one and one from the other, getting close together, and they're going to repel. The electrons from one, the electrons from the other are getting too close, so they're going to repel, right? And like charges repel. So if they begin to repel, that makes them less stable and increases their potential energy. It makes them anxious, right? They don't want to be there and they want to get apart. Okay. So a happy medium or stable bond length is reached at a distance where the forces of attraction and repulsion result in the lowest, most stable potential energy. And that's this chart here. And we've seen this before where we looked at and we said, well, here my two atoms of hydrogen are too close together. They have a really high potential energy. But as they start to spread apart, well, then all of a sudden they get to the sweet spot, which is the minimum potential energy of the bond between them, of their attraction. We look over, it's at negative 436 kilojoules. But then as I start to continue to pull them farther apart, well, now they lose potential energy because they no longer feel any sort of attraction between them until eventually it gets to zero when there's no attraction at all. They're just too far apart to even know that the other one exists. Okay, so we've talked about bond length, which is the distance between the nucleus of one and the nucleus of the other, and their bond strength, which is the potential energy of this bond, okay, of the bond here. We abbreviate this BDE, the bond dissociation energy, or the strength of a bond. And we've also talked about how triple bonds have the most electrons involved, so they're the shortest and the strongest bond. And then opposite of that would be our single bonds, which are the longest and the weakest bond. So if I were to look at the bond energy of hydrogen, hydrogen's a diatomic of two hydrogen atoms bonding together. Well, the bond energy, or the strength of my bond, is its potential energy. So I would read this chart and I would see that my bond energy is the lowest point. I read across, so that is 436 kilojoules. And it's positive because that's the amount of energy stored in there. We're not breaking it, we're not releasing it. So that's just the amount of energy stored in the bond. It's going to be positive. Now, every type of bond is going to have a different bond dissociation energy. So if I were to look at, for example, CH4 is this. It's methane. Okay. Every one of these bonds is going to have a slightly different bond dissociation energy because using different electrons, it's in a different position in space. And as I start to remove hydrogens, I'm going to change my bond energy that I have. So it's important to note that while, yes, each one of them has a slightly different bond dissociation energy, we can see they range from 460 to 340. But if I were to have to look at every single one and think about, was this the first one or the second one or the third one, it would get to be quite a bit. So what we do instead is we take the average bond dissociation energy for a class of bonds. So we say, well, we could look at each individual carbon-hydrogen bond, or we could instead take the average. So the average of all four of these is 415. And that's in kilojoules. And so we say that, well, really a carbon-hydrogen bond has an average bond dissociation energy of 415 kilojoules. And so that's what we use when we're calculating bond energy. Now let's think about what happens if we break a bond versus forming a bond. Well, to break a bond, remember, bonds are happy. They're at this minimum potential energy. They want to stay there. So it takes energy to break a bond, right? We have to put in energy to pull them apart, to break them. So if I have to put energy in, that makes it endothermic. My change in energy is positive because I'm putting energy into my system, which gives me a positive delta H, or positive bond enthalpy. Oppositely, or conversely, if I'm forming a bond, bonds want to be formed, right? They want to be at this low energy. So energy is released, right? I released energy to get here, right? We know it's at a negative potential energy. Energy is released. If I'm releasing energy, that's exothermic. Therefore, my change in energy is negative, results in a negative delta H. So if I was looking at a chemical equation, I need to break bonds. So I need to put energy in. And then after I have all these broken bonds, they're going to come together and form something new. And when they come together and form something new, energy is released and I'm making bonds, or I'm forming bonds. So we can write this out in a mathematical equation. My delta H, my bond enthalpy, is equal to the sum of the energy required to break my bonds plus the sum of the energy released when I form my bonds. Now, when I break bonds, I have to put energy in, so these are all positive values. And when I am forming bonds, energy is released, so these are all negative values. And you will see, is this one on there? Nope, this one is not on your list. Okay, not on our formula chart, which is unfortunate, but it's not. So if we remember that it takes energy to break bonds, so that's positive, and we release energy when we form bonds, we just need to add up all of our average bond dissociation energies for all the bonds broken, and then plus the amount released, so negative bond dissociation energies for all the bonds being formed. We can then determine if our reaction is endo or exothermic by looking at the number of bonds that are broken and the number of bonds that are formed. If we break more bonds than we form, so my bond enthalpy of breaking is more than the bond enthalpy of forming bonds, that means it's going to end up with a positive delta H, so it's endothermic. And that means that my surrounding temperature drops because I'm pulling in energy from the surroundings to break my bonds. Okay, so the surrounding temperature drops. If my energy, my bond enthalpy for breaking bonds is less than the amount released formed bonds, so I'm releasing more energy than I'm putting into break, overall it's going to be exothermic, which means I'm releasing energy into my surroundings, so the temperature of my surroundings increases. All right, let's put this into practice. Here is a chart of a whole bunch of bond energies, okay, for various bonds that we can have. If we need other ones, we can look them up in a chart. That's easy. So instead of having multiple pages, we just have a few of them that we'll use. So this asks us to calculate the energy change of the reaction below. Well, first we need to figure out what bonds do we have, what are being broken, what are being made. So we need to draw Lewis structures. So we have things written like this, CH3CH. That means I have a carbon with 3 hydrogens around it. That's my CH3, linked to a carbon with a hydrogen, double bonded to another carbon, and then 2 hydrogens coming out. Then I have H2, so 2 hydrogens together. And then I make CH3, so carbon with the 3 hydrogens, linked to another carbon, 2 hydrogens, so one comes up at the top, one at the bottom, to another carbon with 3 hydrogens, like so. So I need to look at what these are all going to be broken. And we know that it takes energy to break them. So these are positive values. And all of these bonds are getting formed. And we release energy when we form bonds. So these are all negative values. Okay. So I have carbon-hydrogen bonds. I have carbon-carbon single bonds. I have carbon-carbon double bonds. I think that's it for this guy. And then I have a hydrogen-hydrogen single bond. In terms of ones formed, all of these are carbon-hydrogen bonds. And in the middle, I have carbon-carbon bonds. So those are the types of bonds that I have. The number that I have is also important. So in terms of carbon-hydrogen bonds, I have 1, 2, 3, 4, 5, 6. So here I have 6 of these. I have 1 carbon-carbon bond. I have 1 carbon-carbon double bond. And I have 1 hydrogen-hydrogen single bond. In my product, in terms of carbon hydrogens, I have 1, 2, I have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 carbon hydrogen bonds, and I have 1 carbon-carbon here, 1 here. So 2 carbon-carbon bonds. So my energy in this carbon-hydrogen bond, I look on my chart here. Carbon-hydrogen is here. It is 412. So 6 times 412. Carbon-carbon single bond is 1 times 348. Carbon-carbon double bond is 612. That makes sense that this one has more energy than my single bond because it's a stronger bond. And then my hydrogen-hydrogen is 436. Okay. Formed carbon-hydrogen is still 412. And this is being formed, so it's negative 412. So it's being released. And then carbon-carbon is 348, so negative 348 because, again, energy is being released. So we could write this like this, or you'll see it commonly written as we'd have 6 times 412, right? We want this means the sum of the delta H of the bonds broken. This means the sum of the delta H of the bonds formed. So bonds broken, 6 times 412 plus 348 plus 612 plus 436 equals, and I did this a minute ago, so 3868. This is in kilojoules per mole. And then my bonds formed, I have 8 times negative 412 plus 2 times negative 348. And when I do that, I get negative 3,992 kilojoules per mole. So these added together gives us my overall bond dissociation energy for my system. So I have 3868 plus a negative or minus 3,992 means that overall 124 kilojoules per mole. So what does that mean? That means that this is an exothermic reaction. So energy is a product. So we could have this written in terms of my products up here. We could say, this might say plus 124 kilojoules per mole. Okay, we could see that. Or we could see it as delta H is 124 kilojoules per mole. Sorry, negative 124 kilojoules per mole. And we also, if I were to do this in a beaker and then touch the beaker would feel hot. So the surrounding temperature would increase and it would feel hot. Okay, because I would feel the energy leaving or being released from the forming of my new bonds. So we'll practice more of that tomorrow. And we'll do more calculations. We'll draw some more structures and we'll dig into why this is what it is.